Okay, so beyond panel designs, we'll first talk about regression discontinuity. Um, this is something you've probably seen and maybe done yourselves. The generalized version of this relies on thresholds for program participation. It's really the origins of this design in the public econ literature, looking at program participation based on scores, where there is some threshold that determined eligibility, and units near that threshold were likely to be similar, other than, of course, which side of the particular threshold they were on. And prior uses typically associated with cutoffs based on scores, indices, baseline measures, etc. This kind of eligibility ranking. There's also an extensive literature that thinks about what the optimal bandwidth, so how far away from that threshold we want to include observations, how to deal with fuzziness where the units are not actually perfectly aligned with that threshold, but are on either side of the threshold with some other either random or non-random elements. I think the more interesting case for us is the recent growth in uses based on spatial cutoffs, boundaries, whether formal boundaries or informal boundaries. A really nice example is this one from Brazil by Baraguana and Bai. This is a good example of a case where the program is restricted to eligible areas like administrative units that are, again, well-defined in space. This is a nice RD corollary to the example I showed yesterday, where we had ourselves run a panel model on many of these same indigenous communities whose land rights were formally recognized in the Amazon. So in this particular case, the authors have on the right-hand graph, there is the red boundary of the actual indigenous community's lands, and the blue buffer is essentially the 12-kilometer buffer inside and outside of that border. And these authors are going to essentially look for big differences in treatment effects that are happening based on the whether that unit is on the inside or the outside of that border. Again, because they've got this into grid cells, they can look individually at grid cells based on their distance from the border, or the distance of that center of that grid cell to the border itself. So this is kind of, I think, one really nice example of this. Another example comes from this Jones et al. Paper that just came out in the AER. Really great work by a great group of folks. You probably know some of these guys. This is a case where rather than a formal boundary, this is where geophysical features cause differences in treatment reach that are otherwise apparently random. In this particular case, irrigation in Rwanda, the irrigation canals and lines were determined by geophysical features. So in this particular case, this was the slope necessary to maintain good flow through the canal origins and then down to the bottom of the destination. And as a result, the particular routing was as good as random, and created big differences between those just downhill from the canals to those uphill from the canals. And as a result, we've got big differences that we can exploit for causal impact estimation. That right-hand side shows you differences in irrigation shares of fields just essentially downhill, so in the command area, to those outside the command area, to just uphill of these otherwise arbitrary lines determining the irrigation flow. So these are, I think, two really nice kind of examples of how we can exploit RD in these cases. This particular case is also one where the authors purposely oversampled around the discontinuity. So they knew about the existence of the discontinuity, and they collected primary data directly from units along the discontinuity. The prior example from the Brazilian Amazon is one where the authors relied on remotely sensed data. And that's particularly helpful, again, for discontinuities because it gives you much more density along the discontinuity. Otherwise, we're often in this world, if we're relying on secondary data or just a representative sample, but not one with any real oversampling around the discontinuities, where we might not have enough power to really detect the jump at the discontinuity. Again, this is something that the potential advantage of either remotely sensed data or understanding the geospatial layout of the intervention before collecting the primary data. We'll say some things to think about. Again, as with all designs, this relies on non-interference across the boundaries, so not spillovers, but there are many channels that through which this might happen. So, for example, that Bargwath and Bailly paper we just looked at, certainly the potential for spillovers to happen across the boundaries of the lands of these indigenous groups. So whereas it might have been the case that it would have been lands just on the inside would have been deforested previously, that the drivers of that would not be placed at the outside of those lands. So definitely some potential for interference in that kind of design. This really nice new paper by Cornwall and Solly that tries to relax this assumption and account for network and peer effects in a spatial model. It's not widely yet in use. So I think in many of the cases we're seeing for RD, there's definitely a concern about spillovers and something we should pay extra attention to. We'll talk more about spillovers a little bit later. As I just mentioned, RD relies on dense spatial coverage of outcomes around the specific boundaries. So that's a big advantage of remotely sensed data. There are also many cases where the boundaries mattered, quote unquote, for the outcomes even before the intervention. So that we're back to relying on differences in differences rather than just single differences across the boundaries to account for any non-comparability at baseline. Right? A lot of these boundaries are meaningful boundaries, not just for the intervention, but for many other factors. One example, again, with rehabilitated irrigation perimeters in Afghanistan that we looked at, areas inside the rehabilitated irrigation perimeters were different from the start, partly because there had already been perimeters there that are now being rehabilitated, right? So we want to rely again on some combination of RD together with panel or different diff models to tackle this kind of situation. In addition to RD, we can also think about matching as a complement to both of these, both RD and panel designs. Lots of prior uses of matching that attempt to account for the baseline differences between the samples of treated and untreated units. The more recent version is to not, again, typically use it on its own, but in combination with differences in differences to essentially prune the samples to only units that are comparable based on these variables we're using for the matching. This is particularly important, we think, for a lot of GIE work and remotely sensed data more generally, because exactly that benefit of remotely sensed data having wide spatial coverage, being able to see stuff about units that were not in the initial survey sample or initial survey design, that is a blessing, but it can be a real challenge because now we have a much wider pool of potential comparison sites from which to select, and narrowing those comparison sites to those that are most similar to the treated units. Again, that's something that matching is well designed to do. So again, the kind of way that we're seeing this happen is that we're using the matching to prune as a pre-processing step the samples to only the potentially comparable samples on which we then run the panel models that we just looked at. So again, that's the canonical approach. It does, it's pretty off the shelf and pretty easily translatable when you have a single treatment period. But when we have multiple treatment periods, like those rollout designs we just looked at, most of the existing matching routines are not kind of built to handle that right away. So it frequently requires reducing the time periods into binary windows like early versus late treatments, and then running the matching algorithms on this particular binary indicator of treatment. And then after having reduced the sample that way, actually then going back and running the standard multiple treatment times models on that pruned or reduced sample. So that's the way we're using matching more and more these days. Turning then from RD and matching to natural experiments, lots of other geophysical features and drivers of program placements that are not correlated with outcomes. Things like hydrological constraints that shape where water flow can be. So, the RD version that we just saw in Rwanda is kind of an example that picks up part of this variation, but some really great work from Brazil as well, Lipscomb et al. And Assunção et al. That uses the hydrological constraints to determine where hydropower dams can be built, to then trace the effects through to electrification access. So communities in the immediate area are more likely to receive transmission and distribution extensions, and as a result to have access to power. And this then drives ensuing changes in agricultural productivity and deforestation in areas particularly close to points of the rivers where the hydrology made hydropower dams much more feasible. And as a result, growth in ag productivity and forest loss in those particular areas, again, due to the hydrological features of the river flows rather than to other factors. Also lots of work in India and other places, thinking about highways and their routing as natural experiments. The golden quadrilateral routing of main highways in India between main cities essentially means that intermediate locations, villages and towns on the direct route between major cities like Mumbai and Delhi are much more likely to essentially receive the transportation upgrading and improve market access from these highways. And that then different folks have leveraged to look at a variety of outcomes, including wealth and welfare, but also forest loss in those particular communities as the market access drives their ability to essentially take forest products, timber, et cetera, to allowing markets. So lots of work in this area as well.